All right, good afternoon. Today we're going to look at a couple of models for our diode devices. So diode is a semiconductor device. It's a nonlinear device. Nonlinear in this case means that the voltage and current for a diode have a nonlinear relationship, unlike a resistor. It is still a two-terminal device, right? Um, and as with most semiconductor devices, we can only Well, most semiconductor devices, if we try to analyze them, there's a variety of environmental factors we need to take into account, and the analysis is not easy. So we use a variety of models to best suit our needs. So two of the most common models that we look at for diodes are the ideal diode models and the constant voltage drop models, otherwise known as CVD model. So let's take a look at both. They're both very similar. The only difference between the two is in forward bias. So CVD approximation model in an ideal diode model. Let's talk about what those are. Okay, so as I was saying, a diode, as we know, is a two-terminal device. It's a semiconductor device, and unlike a resistor, capacitor, or inductor, it is a non-linear device. This is the anode, this is the cathode. Diode voltage is always referenced with positive at the anode and negative at the cathode. And diode current is always reference, again, positive at the anode, meaning it's going from anode towards the cathode. Simple way to remember, of course, is the arrowhead. All right, so the ideal diode model and the CVD model, both models have similarities. What we are doing is we are modeling the diode as a switch, right? We learned about the switch and we discussed a little bit about switches in the previous lecture. So we are modeling the diode as a switch that has an on state and an off state. Okay. So diode is modeled as having two states, on and off. Okay. If it's on, we model it as having, not having, sorry, we model it with a short circuit wire. So it's replaced with a short circuit wire. When it's off, like an off switch, we replace it with an open. Okay. Replace it with an open. So again, the two terminals of the diode are replaced with a short circuit wire or connected with a short circuit wire. And in case if it's off, then we simply open it up. Okay. So if a switch is open, can current flow through it? No, right? So the same thing, if a diode is modeled as open, no current can flow through it. So ID is 0. Okay, ID is 0. Diode voltage is modeled as being not modeled is less than 0 volts, meaning it has a negative voltage when measured with positive at the anode and negative at the cathode. Diode voltage VD would return a negative value. Okay, that's what would happen if the diode was off. Now, if the switch is closed, you want to turn on the light. So you press a switch is closed. What is the value of the voltage across the two terminals? A closed switch is replaced with a wire connecting both nodes or both terminals. Voltage is defined as the difference in electric potential between 2 points. If the 2 points are connected with a wire, they're electrically the exact same node. That means there is no difference in electric potential between those 2 points. So voltage is 0. So in an ideal diode model, if your assume diode is on, then diode voltage is 0 volts. And because it provides a pathway for current to flow through, ID has a positive value, and so it's greater than 0. Okay. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Okay. Does it make sense so far? All right. Okay. So the CVD model, constant voltage drop. We'll get to these graphs in a minute once I finish with the explanation. The CVD model is exactly the same as the ideal diode model, especially in the off state. Okay. So in the CVD model, when the diode is off, it is an open. That means does not allow any current to flow through. No current flowing through. ID is equal to 0. So constant voltage drop or CVD model is very nearly the same as the ideal diode model, except for a few differences. So let's start with the off state first. When it's off, it's open. ID is equal to 0 amps. Okay, we'll talk about voltage in just a little bit. However, okay, let's wait. Okay, however, in forward bias, it is modeled as a voltage source with a value equal to the diode turn-on voltage. So when it's on, it is replaced with a short plus a voltage source. And the voltage source has a value that is equal to the diode turn-on voltage. Okay, and the turn-on voltage could be 0.6 volts, could be 0.7 volts. It would be specified in the problem itself. All right, and those are the two big differences. Now, let's take a pause. Let that sink in. Let me know if you have any questions. Okay. All right, let's look at the graph now. That's the ideal diode model. What do we see? Well, the one in blue first is the characteristic of a real diode, real or practical diode, right? Does not turn on. Once it turns on, current increases at a rapid rate. Not exactly a straight line going towards the top. Okay. But in an ideal diode, what we do is, since we are modeling the diode turning on and voltage is equal to 0 in forward bias, one in red is representing the model diode, meaning the ideal diode model. Current ID is 0 when the diode is in reverse bias, right? And then voltage is 0 right here when it's in forward bias. And so you have two lines simply joining, forming a right angle. That's all the ideal diode characteristic is, lying on the y-axis and the negative x-axis. So line pointing straight up on the y-axis is the diode in forward bias, meaning in the forward region, it's on. Diode is a short, voltage is equal to 0, current is equal to the value that is flowing through it. And the negative y-axis, negative x-axis indicates the diode is off. There is no current flowing, and the voltage across the diode negative. Okay, that's the model characteristics in red. In CVD model, everything remains the same except there is a shift. There's a shift to the right that is equal to the turn on voltage. If 0.7 volts is required to turn on the diode, then the vertical line, which is indicating the current flowing through the diode, is shifted to the right. Okay, that's this one right there. Again, ideal diode, constant voltage drop. Both models are nearly the same. The only difference is that it requires a certain amount of voltage to turn on when it's forward bias. So constant voltage drop model, CVD model, requires 0.6 to 0.7 volts. Other than that, both models are the same. Okay, let's take a pause. Let me know if you have any questions. Does everybody understand the difference? Does everybody understand the model and the difference? Okay. So one final thing is, what does it mean for the diode voltage when it's off? It can't just be less than 0, right? Because if it's 0.5 volts, in an ideal diode model, 0.5 volts is sufficient to turn on the diode. However, in a constant voltage drop model, the diode is still off. So diode voltage is less than the turn on voltage. Okay, VD is less than turn on voltage. That's what it is. So the way we use these is by making assumptions at the beginning of our analysis. So here's an example. We won't be able to get into the example, but I want to outline the steps that we would use. This example, VRD circuit, you have a diode, you have a resistor, and you have a voltage source that is driving the circuit. Output is taken across the diode itself, and we are modeling the diode as either on or off. Okay. So now the steps for this remain the same for both models. I'm going to write it for the ideal diode model, but it remains the same for the CVD model also, right? It doesn't change. So ideal diode model or the CVD model. The first thing to do is to assume a diode state. Is it on or off? Now, you can choose any state you want. There's only two, right? So you perform two analyses at most. When you first make the assumption, you look at the circuit, you observe it, and strictly from observation, you can assume a state. In this case, we have the positive terminal of the voltage source being applied to anode. More likely than not, the diode has to be on. So we would assume that it's on, right? Then the second thing to do is replace the diode with its equivalent. Meaning if you assume on, then you replace it with a short circuit. If you assume that it's off, then you replace it with an open circuit. So replace the diode with its equivalent. Based on your assumption. Okay. Based on your assumption. Then you analyze and you determine the voltage and current. Meaning if you assumed on, then the resulting current must be positive or greater than 0, and the resulting voltage must be equal to 0. If those two conditions are not met, then your assumption is incorrect. Then you go back to the top, you change your assumption, and you reanalyze again. You perform your calculations again. And so you analyze and you determine the voltage and current, and then check or verify your results against your assumption. Okay. You verify it against the assumption. So in a way, it is kind of like an iterative analysis, but it's a logical based assumption first. Okay. All right, questions? Does everybody understand the concept? Okay. All right. Okay, we'll end class here today and we'll pick up here again on Wednesday.